An electrolytic cell is an arrangement in which an external source of voltage brings about a chemical change. Since electrical energy is put in, the reaction is non-spontaneous. When you recharge a battery, you are actually running them as electrolytic cells. Let's look at a simple electrolytic cell. As shown in the diagram here, it consists of two copper electrodes immersed in an aqueous copper sulfate solution. The electrodes are connected to a DC power supply. When the power supply is turned on, reduction occurs at the cathode, which is the electrode connected to the negative lead of the power supply. Oxidation occurs at the anode, which is connected to the positive lead of the power supply. The reduction half reaction at the cathode has copper 2 ions gaining 2 electrons to form metallic copper. At the anode, copper metal undergoes oxidation by losing 2 electrons to form copper 2 ions. Students often find it difficult to remember the difference between galvanic and electrolytic cells. In galvanic cells, the anode is considered to be the negative electrode, and reactions are spontaneous. The cell potential is always positive, and the change in Gibbs free energy is negative. In electrolytic cells, the cathode is considered to be the negative electrode, and the reactions are non-spontaneous. The cell potential is negative, and the change in Gibbs free energy is positive. Remember, in any cell, oxidation occurs at the anode and reduction occurs at the cathode. For example, an impure sample of copper can be used as the anode. As the cell runs, pure copper is deposited on the cathode. Less reactive metals such as silver and gold and non-reactive impurities fall to the bottom as anode sludge. Similar processes are used to produce sodium, magnesium, aluminium, and other metals on large scales. Michael Faraday was the first scientist to quantitatively study electrolysis. Faraday's work can be summarized in his 2 laws of electrolysis. Faraday's first law states that the extent of chemical reaction that occurs at any electrode during electrolysis is directly proportional to the quantity of electricity passed through the electrolyte. The electrolyte may be molten or in an aqueous solution. In other words, the mass of an element that deposits at an electrode during electrolysis is proportional to Q, the total amount of electricity passed through the cell. Faraday's second law states that the amounts of different substances produced by the same amount of electricity passing through the electrolytic solution are proportional to their equivalent masses. Equivalent mass can be calculated by dividing the atomic mass of a metal by the number of electrons needed to reduce a cation. The amount of charge Q passed through the cell can be determined from the product of current and time. To determine the charge in coulombs, multiply the current in amperes by the number of seconds for which it was applied. The stoichiometry of the half reaction needs to be considered in quantitative electrolysis. The half reaction relates the number of electrons to the metal deposited. For example, in the reduction of silver ions, 1 mole of electrons is needed for each mole of silver ions that reduce. You know that the charge on one electron is equal to 1.6021 multiplied by 10 raised to the power of minus 19 coulomb. Hence, the charge on 1 mole of electron is equal to the product of the charge on an electron and the Avogadro number. This can be written as the product of 1.6021 multiplied by 10 raised to the power of minus 19 and 6.02 multiplied by 10 raised to the power of 23. Therefore, the charge on 1 mole of electrons is equal to 96,487 coulombs per mole. This quantity of electricity is called Faraday, which is symbolized by capital F. Sometimes, this is rounded off to 96,500 coulombs per mole of electrons. Now use all this information you just learned to solve a problem. A 2.50 ampere current is passed through molten magnesium chloride for 15.0 minutes. What is the mass of magnesium deposited at the cathode? Let's work through this problem together. First, we'll find the charge that passed through the cell. You know that charge in coulombs is equal to the current in amperes multiplied by the time in seconds. We need to convert 15.0 minutes into seconds. 15 minutes into 60 seconds per minute is equal to 900 seconds. The current is 2.50 amperes. The charge that passed through the cell is then 900 seconds times 2.50 amperes, which is equal to 2,250 coulombs. From the half reaction, we see that 2 moles of electrons are needed for each mole of magnesium atoms that form. Therefore, we require 2 Faradays, or 2 multiplied by 96,487 coulombs, to deposit 1 mole or 24 grams of magnesium. Therefore, for 2,250 coulombs, the mass of magnesium deposited is equal to 24 grams per mole multiplied by 2,250 coulombs divided by 2 multiplied by 96,487. Thus, 0.2798 grams of magnesium is deposited at the cathode.